Despite major scientific discoveries that provide long support for the Big Bang Theory, there's been a viral paper spreading over the internet lately which says that the James Webb Telescope has refuted the theory. This has led to many to think that our understanding of the Big Bang may be wrong. Could this really be the case? Is the James Webb Telescope rewriting fundamental theories of the cosmos?
So one of the things the Webb can do is it can, because of its sensitivity to longer wavelengths, it can see light that's travelled across the universe for longer, and therefore it can see further back in time. I mean, I should say it will acquire lots of data. It's got many missions and they're all interesting. One of them is to observe the formation of the first stars and galaxies, which is a tremendous problem. We don't really know how the first stars and galaxies formed. We don't really know how those enormous black holes, there's a galaxy called M87 about 55 million light years away, which has got a black hole 6 billion times the mass of the sun in it. 6 billion times the mass of the sun. How did that get there?
According to Brian Cox, regardless of what you may have read or heard, the Big Bang is supported by a preponderance of evidence that has become the most successful theory ever put forth for the origin and evolution of the universe.
In terms of the Big Bang, we very strongly suspect that that was an event in a pre-existing universe. So we think that space and time existed before that, and the universe was probably cold and expanding very fast. And that expansion slowed down, and the slowing down of the expansion is what we call the Big Bang. So that's called inflation. So that's the best theory of what happened before the Big Bang. But what started inflation off, we don't have the knowledge, so we just don't know.
The Big Bang theory was conceived nearly a century ago by following the evidence that the universe is expanding, working out what this might logically mean, and then testing it on predictions such as the existence of the cosmic microwave background radiation. There's been a viral paper spreading over the internet which says that our understanding of the Big Bang may be wrong. According to Brian Cox, the such claim is ridiculous. We can actually see the afterglow of the Big Bang.
You cannot claim that there wasn't a Big Bang. You can pretty much see, we can see the afterglow of the Big Bang. It's called the cosmic microwave background radiation. It was discovered in the 1960s. It is the afterglow of the Big Bang. So you could ask the question, well, how far away do you have to look to see the origin of the universe?
One of the common misconceptions about the Big Bang model is that it fully explains the origin of the universe. Big Bang is a really misleading name for the expanding universe that we see, because we see an infinite universe expanding into itself.
The universe is accelerating in its expansion, which is a great mystery. We thought, well, gravity is always attractive, and so it should be, we've got all these galaxies in the universe, and the universe has been expanding since the Big Bang, and so it should at least be slowing down. And there was even a question as, is there enough matter in it to slow it down so much that it stops and recollapses again? But the universe is accelerating in its expansion, and that it will continue to accelerate unless some new physics appears that we don't understand, and so it will just continue to expand forever.
This has led many to wonder whether the James Webb Space Telescope could answer one of the most fundamental questions we ask ourselves: where did the universe come from? The James Webb Telescope has many missions, but its ability to image infrared has made it a perfect facility to observe the first stars and galaxies form shortly after the universe began.
When you look at where the galaxies are, then they're random in a sense, but there's also some pattern to it. And in particular, they tend to, roughly speaking, lie on circles in the sky. So they're not completely randomly distributed. And we can trace that all the way back to patterns that we see in the oldest light in the universe, which is the light that, if we look as far as we can out into space, then we're looking back in time. We can look so far out into space that we can see the light from just after the Big Bang, about 380,000 years after the Big Bang, actually. And in that light, before there were stars and galaxies, there are also patterns, which are patterns that match on to the way the galaxies are distributed in the sky today. And where did those patterns come from? Well, the best theory we have is inflation, which says that before the Big Bang, in the sense that before the universe was very hot and very dense, it was still there, and it was kind of cold and empty, but expanding very fast. And then that very fast stretch of the universe came to an end slowed down. And in the slowing down, the universe got heated up and all the particles out of which the stars and galaxies are made were created. And so there's good evidence for that.
The Big Bang model does not describe how energy, time, and space were caused, but rather it describes the emergence of the present universe from an ultra-dense and high-temperature initial state. The James Webb Telescope provides an intriguing look at the early universe. It has been conducting science operations for a few months now. It has already made some intriguing discoveries, including the detection of what could be some of the earliest galaxies ever seen that existed just 200 million years after the Big Bang. The James Webb Space Telescope never disproved the Big Bang. Webb's observations are actually supporting the Big Bang model, showing that the first galaxies were smaller and grew larger over time, just as the Big Bang cosmology predicts.
This is a really simple observation. You can almost do it yourself, actually. You can with a bit of quite advanced amateur astronomy kit, but not a big professional telescope. You can do this. So what you do is you look at the light from distant galaxies. So you have a big enough telescope that you can see a galaxy that's quite a long way away, and you look at the light from it. What you find is that for all galaxies that are not too close, then the light is stretched. So if you think of light as a wave, a bit like a wave on water with peaks and crests, then the distance between two peaks gives you the colour. And so red light has got a big distance between the peaks, and blue light has got a smaller distance. And what you find is that from all galaxies that are further away than the closest ones, the light is stretched, so that the colours of the light from the galaxy are a bit redder. And what you find is the more distant the galaxy, the more the stretch. So that's the observation. And that's exactly what you'd expect if the galaxies were riding along on a stretching fabric, the fabric of the universe, if you like. That means that the further away the galaxies are, then the more stretched the light will be. Why? Because it's been journeying through the stretching space for longer, so it's got more stretched. And it's called the Hubble law, actually. It was first observed in the 1920s by Edwin Hubble. So it's a very simple and direct observation.
Astronomers have been so keen to use the new James Webb Space Telescope that some have got a little ahead of themselves. Many started analysing Webb data right after the first batch was released and quickly posted their results on preprint servers, but are now having to revise them. The telescope's detectors had not been calibrated thoroughly when the first data were made available, and that fact slipped past some astronomers in their excitement.
So you have to take data seriously, and you hold it, and you're allowed to have a contradictory position. And what you find almost always is that our worldview is quite sophisticated now, and the key thing is consistent. In the 1990s, we had a measurement of the age of the universe, which at the time, based on the expansion rate we've measured, was about 11.5 billion years. And we had a measurement of the age of systems called globular clusters, which are old star clusters in the Milky Way galaxy. And the age of those was about 12 billion years. And that was the case in the 1990s. So what did people do? They just carried on measuring things. And then in 1998, a physicist who's now at ANU in Canberra in Australia, Brian Schmidt, and another team in America were looking at supernova explosions, and found out that they were dimmer than expected. And it turned out the interpretation was that the universe is accelerating in its expansion. A complete shock. It's like we thought the universe was slowing down. It turned it was speeding up. And that changed our measurement of the age to 13.8 billion years. But there was a time when there was a big inconsistency between the age of the universe and the oldest things in the universe, which were older than the universe.
There are a few mysteries and problems that have been resolved while others are still outstanding. For example, it is not yet understood why the universe has more matter than antimatter. For any theory, one should not hesitate to question every possible assumption, no matter how basic they are. But the new ideas about the universe should not dismiss everything else up until that moment. Nearly everyone in the community of astrophysicists has chosen to work with the Big Bang Theory, recognizing that our efforts may lead to an ever deeper understanding of the universe, where the Big Bang becomes the core idea of something even bigger. Thanks for watching. Did you like this video? Then show your support by subscribing and ringing the bell to never miss videos like this.